Okay, so we can now try problem 3.5 from Wald's General Relativity, where in part A he wants us to show that any curve whose tangent satisfies equation 3.3.2, which is on the right-hand side of the screen there, can be reparameterized such that equation 3.3.1 is satisfied. So let's go ahead and show this. So basically what he's saying is that we can take as a given that TA nabla A TB is alpha T, alpha TB rather. So this is an equation for parallel transport. Which preserves direction, not necessarily length. And what we want to do is show that this can be reparameterized such that SA nabla A SB is 0, where S is going to be our new parameterization. I'm going to put a star on this because I will reference back to it later. Okay, so let's remember that the components of these tangent vectors look like this. dx mu by dt. So what we're going to do is let S mu equal dx mu by ds, which by virtue of the chain rule tells us that it is dx mu by dt, dt by ds. Okay, and with this, let's write down the equation explicitly parameterized by S and see what we get. So let's go SA nabla A SB equals SA times the formula for the covariant derivative here, so nabla, or not nabla, del A SB plus gamma, or the Christoffel symbol, BAC SC. And this is just equation 3.1.15 from Wald. So we can rewrite this like this. Remembering that SA is dxa by ds, we can rewrite this like this. We're actually going to put it right through onto both terms as well. So dxa by ds then we're going to have, okay, let's do it this way, a d by dxa, and we also have dxb, which is the SB here, by ds, or dxb by ds is the SB rather. And then for the gamma term, we can just keep things simple for now. SA, SC. So now I'm going to do kind of a dirty physicist trick here. This is not ideal for mathematicians, but I'm just going to say this, that these dxa's cancel out, and we get here d by ds dxb by ds plus gamma VAC SASC. Or actually, I'm going to rewrite this as SB. Okay, so then we have d by ds. Now remember that SB is actually TB times dt by ds, which we wrote up at the top. Then we get our gamma term again. And we're going to do the same thing over here. These s's are going to be replaced with t's, and we're going to get a square of the conversion factor here, dt by ds. Okay, so we can do a little chain rule on this first term now. So we're going to get one term that's like dtb by ds, dt by ds. We're going to get another term that's tb d squared t by ds squared, so the s derivative is applied twice to t. And then the gamma term just remains as is for now. Okay, so let's do another chain rule here now and say that dtb by ds is actually going to be dtb by dt times dt by ds, but we already have a dt by ds here, so this is going to get squared. Plus, we keep our tb d squared t by ds squared, and the gamma term as is as well. So now we actually have two terms with this dt by ds squared. So let's group those together. Oops. So, okay, we take the dt by ds squared out front, and that's going to leave us with a d, tb by dt plus gamma b ac ta tc, and then plus our term that doesn't have that square. This term has the derivative operator applied twice. Okay. So we're gonna now chain rule this dt by this dtb by dt, and we're gonna say that it's dtb by dxa by dt plus gamma plus that last term. I'm not even gonna write it right now. Now what you'll notice here is that this bracket term, oops, I should have drawn that a little nicer. The bracket term here is actually, let's see. So dxa by dt is going to be a ta, so we can factor that out. We're going to have ta times the partial derivative of tb plus gamma bac tc. But this is nothing other than the definition for the covariant derivative here with ta out front. So we get nabla a tb, which we already know from up here. Where is it? Right here is alpha tb. This was a given. So therefore, we can rewrite our entire expression down here. It's going to be dt by ds squared times alpha tb plus that last term, which was tb d squared t by ds squared. So we can pull the tb out. And we get alpha times dt by ds squared plus d squared t by ds squared. So the idea now is that we are able to pick S such that equals 0. And once we do this, so it's set up this way, and we show that we can pick S such that this is 0, and this is a solvable differential equation. So therefore, can reparameterize such that SA nabla A SB equals 0. Okay, we can try part B now. So he says to let T be an affine parameter of a geodesic gamma, and to show that all other affine parameters of gamma take the form AT plus B, where A and B are constants. So if we're talking about an affine parameter of a geodesic, that means that the tangent vectors to the curve are no longer going to be like this. So remember this from part A, we had equals alpha TB. So this is no longer true in general, because little t is an affine parameter to the curve, to the geodesic. This has to equal 0, which implies for us that alpha equals 0. Although we still have the same relationship for S, so our tangent vectors under the other parameterization still have the relation they did from part A. Okay, so with this, if alpha equals 0, then if we write down our differential equation from part A, which is alpha, the square of dt by ds, plus the second derivative of t with respect to s, equals 0. With alpha equals 0, like we said, this first term goes away, and it simply implies that d squared t by ds squared is 0. So by some very simple logic, then we can integrate, and we know that dt by ds is just equal to a constant, which we'll call c1. They call it a or b, I think. And then, if you like, you can move the ds to the other side, integrate once more, and we find that t is c1s plus c2, or exactly the form that the problem asks us to show.